Hey guys, hope everybody's doing all right. What we're going to do is start off our new unit on chemical equilibrium, and we're going to take a look at something called dynamic equilibrium today, and it has to do a lot with vapor pressure. So on the screen, there are different examples of equilibrium systems. We're going to focus on the one in the bottom left today, and eventually we'll get to equilibrium with solutions and chemical reactions, and it's a pretty interesting unit. So let's get started with the first type of equilibrium system, which again is systems at equilibrium with vapor pressure. So we're going to look at what humidity is first, and humidity is really just the amount of moisture in the air. So if you think about what 100% humidity would be, it's when the air is saturated with water vapor. So that is water in the gas state, right? So a dynamic equilibrium system would be reached if this was the case. So that means the air cannot hold any more water vapor. Okay, it's saturated, right? So you have some water in the liquid state, like we have here in this animation down in the bottom right. And then we have some in the gas state. And you constantly have gas or water going from liquid to gas and gas into liquid. It happens, at the same time. That's what the equilibrium system is. So gas to liquid condensing, liquid to gas evaporation at the same time. And that ends up with a 100% humidity dynamic equilibrium system. So let's take a look at vapor pressure a little bit closer here. We did a little bit of this in our previous unit, but we'll expand on it a little bit. So even at temperatures below the boiling point, some molecules of a liquid have enough kinetic energy to escape the intermolecular forces that hold them together and evaporate. So we talked about that. The more molecules that escape, the higher the vapor pressure that exists. So you can see that there's liquid ethanol in this flask here. And some of that is going to evaporate and turn into a gas. You see that here? And some of it remains as a liquid. This is a saturated system right here in this flask. So you have liquid to gas, gas to liquid at the same time. The gas that's created creates pressure, and that is called a vapor pressure. So the evaporated gas, um, causes that vapor pressure because it exerts pressure on the walls of the container. As more particles exist as a gas, more particles condense back into a liquid, and that's our dynamic equilibrium. So eventually, the liquid and the vapor reach a state of dynamic equilibrium where the condensation and evaporation occurs at the same rate. So that's really neat when that occurs here. And you can see that some of the arrows are going up from liquid to gas and some are going from gas to liquid. Happens all at the same time if we could try to visualize that happening. We call that a saturated solution, a saturated system here. The air is saturated and cannot hold any more vapor. In this case, it's ethanol vapor, okay? So there's only so many gas particles that are allowed to be in here, right? It depends on the size of the flask and the temperature we're at and a couple other factors. Okay, so at this point in the system, we call that saturated. So anytime some more of this ethanol evaporates, some of the gas condenses because we can only have a certain amount in here. You know what I mean? In this system. So we could read vapor pressure by looking at graphs like this. We did this in the previous unit. We looked at it very quickly. So different liquids will exert different vapor pressures due to differing intermolecular forces. So again, we're tying in intermolecular forces from our previous unit, and we're seeing how they affect vapor pressure. So this is the exact curve we looked at in our previous unit. We have diethyl ether, which is very London dispersion-y. Okay, there's really there's no hydrogen bonding there, right? It's more nonpolar. We have ethanol, which has two carbons and then an OH group at the end. Then we have water, which we're familiar with. So we have the three of those there, and actually ethylene glycol down here in green. I always miss that one. The weaker the intermolecular forces, which in this case would be diethyl ether, the vapor pressure is going to be. So we'll review from our previous unit. If you have weak intermolecular forces, that means the particles are more able to go from the liquid to the gas state, right? So if more particles are going to go from liquid to gas, there is more gas. More gas means more air pressure, which means a higher vapor pressure. So remember, it's an inverse relationship between strength of intermolecular forces and the vapor pressure. So weak IMFs, high vapor pressure. Strong IMFs, more particles are, they're more strongly attracted to one another. You're going to have a lower vapor pressure, like ethylene glycol. Very strong intermolecular forces, doesn't evaporate very easily, Since it doesn't evaporate very easily, there are less particles in the gas state, creating a lower vapor pressure. The boiling point of a liquid is actually when the vapor pressure and atmospheric pressure are the same. It's the temperature at which that occurs. So diethyl ether's boiling point is 34.6 degrees Celsius. So at 34.6 degrees Celsius, the vapor pressure of diethyl ether would be equal to 760 torr, or 1 atmosphere, 760 millimeters of mercury, some different units of pressure there. When the vapor pressure equals atmospheric pressure, and atmospheric pressure is 760 torr, the temperature at which that occurs is the boiling point. So you can see 34.6 for diethyl ether, 78.3 for ethanol. Your stronger intermolecular forces here with water, your hydrogen bonding has 100 degrees Celsius. Then ethylene glycol is bigger, has some more stronger IMFs. It'd be a much higher boiling point. Like we have to extrapolate this because we can't see the rest of the graph, right? Okay, so I already talked about this. Normal boiling point is the temperature at which the vapor pressure is 760 torr, okay, which is atmospheric pressure. So, a couple application questions here. What would be the vapor pressure of ethanol in a half-filled bottle of ethanol at 60 degrees Celsius? Here's ethanol. Okay, so I said it has 2 carbons and an OH group. When you take organic chemistry, you'll be more familiar about that. It's a half-filled bottle, so that's important. So let's say we have, I'm just going to use like a flask as an example here, and I can't draw. Like we're all well aware of this. Okay, so here's my half-filled bottle of ethanol. That's important because what does half-filled mean? Half-filled means we have half of it in the liquid state. Okay, so we have half of it in the liquid state and the rest of it in the gas state. Okay, that means we have a saturated solution. Okay, so we have a saturated solution, which means we have liquid to gas and gas to liquid occurring at the same rate here. Okay, so we have a vapor pressure. This chart or this graph gives us the vapor pressures of saturated systems. So we need to make sure that we have some liquid present in order to read this properly. So it really doesn't matter if it's half filled or 3/4 filled, or there could be literally one drop of liquid ethanol in that flask. The vapor pressure would be the same. Okay, as long as you have some liquid state, and then whatever you have in the gas state would be your vapor pressure. So we're at 60 Celsius. That is right here. Okay, and we have ethanol, so we go up to ethanol. Looks like we're at about here. Okay, and then we go over to the y-axis. This is not straight, but we could be close enough. Looks like we end up with like what? Here's 300 is between 200 and 400, so we're maybe a little above that. It's like maybe 310. I don't know, something like that. 310 torr. All right, so we could take a look at something like that and get our vapor pressure. So it's not that difficult here to read this. You're either going to the x or y axis, moving over, and then going to your other axis, right? So not that bad. So here's butanol. What would you predict the vapor pressure of butanol to be at 40 Celsius? Okay, so this was ethanol at 60, and here we have butanol at 40. All right, so butanol is like not on here, but compared to ethanol, ethanol had 2 carbons and then an OH. So let's look at ethanol at 40 Celsius. 40 Celsius up to ethanol and over. So for 40 Celsius, ethanol, a saturated solution, would be like what? 170 torr. Okay. Now look at butanol. Butanol has 4 carbons and the hydrogen bond at the end. So there's definitely a bigger molar mass here involved, right? So both of them have London dispersion, dipole-dipole, and hydrogen bonding as their IMFs. But butanol is definitely bigger, more massive, and therefore more what? Well, it's more polarizable. So we're going to say that the overall intermolecular forces in butanol would be larger. Okay, so go back to what I had on a few slides ago. The greater your strength of intermolecular forces, the lower your vapor pressure is going to be. right? So butanol is held together with stronger IMFs. It doesn't evaporate as easily at 40 degrees Celsius, or really any temperature for that matter. So we want to compare our vapor pressure of butanol with the vapor pressure of ethanol at 40 degrees Celsius. So we said ethanol is around 170 torr at 40 Celsius. So knowing that butanol has stronger IMFs, would it be greater than or less than 170? Well, the answer is obviously less than 170 because stronger IMFs mean a weaker, or I'm sorry, a lower vapor pressure, right? So the answer would be less than 170 torr for that one. All right, let's see what's next. So some water was squirted into a sealed bottle at 80 Celsius. What would the vapor pressure be of the water? So water is squirted into a sealed bottle at 80 Celsius. So we're at 80 Celsius. You go up to the water curve. Okay, and if we go over to the y-axis, we're at like somewhere around 380, 390, right? So let's say 390 torr. All right, so we have to make an assumption here though. It says if some water was squirted into a sealed flask at 80 Celsius, what would the vapor pressure be? What assumption do you think needs to be made here? We need to think about what this is. Like this is the vapor pressure when we have a saturated system, right? So we need to assume that some water isn't evaporating, right? We need to assume that in our flask, we have some water in the liquid state still there. So we could have our dynamic equilibrium, we can have our saturated system where you have evaporation and condensation occurring simultaneously, right? So just something to keep in mind as you go through these and read these. If you don't have a saturated system, it becomes a lot more difficult to answer the question. So that's what we're assuming here on this one. And that's basically it for that problem. It's the main thing I want you to get out of that was it didn't specifically say that in the problem, but we can make that assumption, and usually that's the case. All right, we're going to go through a bunch of practice problems here, and we'll see how it goes. You guys will end up trying some on your own on a little homework assignment or some more practice. But I'll go through some with you guys that are maybe a little bit more in depth that you have to think about. So here is vapor pressure question number 1. It's applying everything we have talked about so far. So a vacuumed flask, that means it's evacuated, right? So it's completely empty. There are no gas particles in there. It's in a 20 degrees Celsius chamber. A sample of diethyl ether, which is on our chart, is squirted into the flask. You can see it here. The flask is sealed shut. After 10 minutes, the pressure in the flask has equalized with some liquid remaining. Really important point there. What's the total pressure in the flask? All right, so this one is pretty simple because we have some liquid remaining. So here's our diethyl ether, liquid state. After 10 minutes, long time to wait, but making sure we wait long enough. Some of it evaporates, right? We have gas particles in here. Okay, so a couple gas particles in there. After that 10 minutes, like we still have these gas particles in here, but some are condensing back into a liquid, right? And at the same time, some of these liquid particles are turning into a gas. All right, so there's our dynamic equilibrium system here. What's the total pressure in the flask? Well, this is easy because the flask was initially basically at a pressure of 0. There was nothing in there. So we're at 20 Celsius. We could assume that since we're in that 20 degrees Celsius chamber, it's in some chamber here, right? That's at 20 Celsius. So everything here is 20 Celsius, right? Go to 20, go up to diethyl ether and over, best I can. And we're at, so 500 would be here. Looks like we're at maybe 450 torr. So we can say the total pressure in the flask is 450 torr, and that is solely with diethyl ether vapor. Okay, so pretty simple stuff there for that one. Question 2. Move on to that one. A flask is placed in a 60 degrees Celsius chamber with the air pressure of 800 torr. So there's already something in here that's giving us a pressure of 800 torr. Ethanol is squirted in the flask with water. The flask is sealed shut. After 10 minutes, pressure is equalized. Some water and ethanol is still liquid. All right, so down here we have water and ethanol in the liquid state. What's the total pressure in the flask? So we have to think back to gas laws a little bit for this one. So if we have a bunch of different gases in this flask, which we do, we have our air pressure of 800 torr. All right, 800 torr air pressure was where we started. We also have air pressure from the liquid ethanol. Okay, so we have ethanol vapor now. So we want to add up what that ethanol is going to be. Right, we also have water vapor. Okay, so the total, the total pressure is the combination of those three. This is Dalton's law of partial pressures, right? If we remember that at all from Chem 1. So the total pressure, P total, that's the pressure of gas number 1 plus the partial pressure of gas number 2, partial pressure of gas number 3, and so on and so on. So we have 800 torr from our standard, like our normal air, whatever was in there. 60 degrees Celsius liquid ethanol. So 60 Celsius liquid ethanol, we are here, follow it over, and we have about, I'd say 300, I don't know, 320. Okay, let's say 320. 320 torr from the ethanol. Do the same thing for water. 60 Celsius to water and over. Okay, looks like we get about, I don't know, 160, 170. Let's just go with 160. Okay, add them up, and you get a total pressure of 1,280 torr. Okay, so it's just Dalton's law of partial pressures. Inside this flask here, this is a total mess now, but inside this flask, we have our air pressure, whatever that was. We have vapor ethanol, and we have water vapor, right, making up those three partial pressures to add up to 1,280 torr. Okay, not too bad. And I actually have, it looks like I have the solution pop up here. Look at that. Okay, 1,280. A little bit more organized than what I had. Okay, here's the official looking Dalton's law of partial pressure equation. All right, number 3. Let's take a look at what this one is. Okay, so a flask has 600 torr of pressure from diethyl ether placed in a 27 degrees Celsius chamber. Okay, 4.5 grams of liquid diethyl ether is squirted into the flask. Flask is sealed shut, 10 minutes pass, pressure is equalized. What is the total pressure in the flask, and does any liquid remain? And if so, how much? So our flask is 600 torr of pressure from diethyl ether at 27 Celsius. So let's see here. We're at 600 torr on my y-axis here. 30 degrees Celsius is here, right? So 27 is about here. I guess I'm going to go up best I can. Okay, and pretend it's a straight line. All right, so I go straight up from 27 Celsius to my diethyl ether curve. I go over, and look, at 27 Celsius, diethyl ether should have a vapor pressure of 600 torr. That's saturated. Like this line, right, this curve is when the solution is saturated. So once you've hit that saturation point, no more liquid could evaporate. Okay, so we have our 600 torr of pressure from diethyl ether in this flask. Okay, at 27 Celsius. At 27 Celsius, the pressure cannot go above 600 torr. If you add more stuff to it, if you add more diethyl ether at least, it can't evaporate anymore because we've reached the saturation point. Remember, saturation point is when the air can't hold any more vapor of that particular gas. So if I add 4.5 grams of diethyl ether into this, what is the total pressure in the flask? Well, guess what? It's still 600 torr, okay? Because I'm already saturated before I added anything to this. Okay, does any liquid remain? Yeah, the 4.5 grams of liquid will remain on top of whatever liquid was in there. It doesn't tell me. So maybe I had liquid in there, or maybe I just had, it was perfectly at that saturation point where there was no liquid there to begin with, and we were at 600 torr. Either way, I know I was saturated, okay? So this is a really easy question if you understand what it's asking. So you're saturated already. Any additional solution or substance, I guess, won't change that pressure because we're saturated. Let's say, for example, we were at 27 Celsius and the air pressure was 500 torr. Well, at 27 Celsius, 500 torr is here, okay? Well, I'm unsaturated, right? So I could add more until the pressure reaches 600, and then it wouldn't evaporate anymore. Okay, so pretty easy. You just gotta think it through. If you know what I mean by saturation and what that entails, then you can just think these through. Okay, number 4. A 65 degrees Celsius flask has 300 torr pressure from ethanol gas, is placed in a 25 Celsius chamber. What happens? When did it start? So 65 Celsius flask, 300 torr from ethanol. Let's find it. 70 is here, 65 is here. Ethanol, we go up to, let's see, 300 torr. So where are we here? 65 straight up, 300's about here. Okay, this is where we are. Okay, this point, this very asymmetrical point I'm making, that's where we are on this curve. So we have a flask with ethanol in it at 65 Celsius, and the pressure in this flask is 300 torr. We are not saturated, okay? If we had a pressure of about 400 torr, we would be saturated. So what does this tell me? This tells me that all of the liquid ethanol I placed in this flask has evaporated, okay? Since it all evaporated, I have a partial pressure or a pressure of ethanol of 300 torr. No more liquid is there to evaporate to make that pressure go up, right? At 65 Celsius, the pressure could be higher, but there's not enough liquid for that to happen. There's not enough for it to evaporate. So literally all of the liquid has evaporated, okay? So we just have a flask full of ethanol gas that's evaporated, and the pressure is 300. I take that flask and move it to another chamber at 25 Celsius. Okay, what happens here? The temperature is going to decrease, right? So let's take where I am on this point, and let's move to the left as I make my temperature lower, okay, toward 25 Celsius. So I'm cooling it, I'm cooling it, I'm cooling it. I eventually cool it off to 25 Celsius, right? But something happens when I reach this point here, right? As I cool the flask, okay, I hit the ethanol curve right here, okay? So at about, I don't know, maybe 55 Celsius, I end up with a saturated solution, okay? As I cool ethanol down, or as I cool any of these things down, the amount of gas that the flask can hold decreases, right? You can see that my higher temperatures have a higher vapor pressure, more gas. As you go down, my lower temperatures have a lower vapor pressure. It holds less. So as I go from 65 and I reach that 55-degree mark, I have a saturated solution. Now, as I decrease my temperature, look what happens. I could only maintain that saturated solution. Okay, so this isn't really going to happen here, right? I maintain my saturated solution all the way down to here, where I'm at that 25 degrees Celsius mark. Okay, so my vapor pressure will start to decrease, and it started to happen at about 55 Celsius. I have an animation here, I think. You'll actually see condensation occur at about 55 Celsius because we're at that saturation point. So as we cool it, the air in that flask can't hold any more ethanol gas, right? So it has to come out of the air. When it comes out of the air, it turns, goes from gas to a liquid. So we'll actually start to see drops of ethanol form on the flask and then roll down the side and create an actual liquid amount of ethanol here. Okay, so that's what is going to happen for this one. So again, these lines here, these curves, tell us how, like, what the saturation point is basically. That's the maximum vapor pressure at a specific temperature these substances can have. Any extra substance you have in there will be in the liquid state, which doesn't really add to that pressure. All right. Number 5, as we kind of wrap up some of this here, if 0.034 moles of liquid diethyl ether is placed in a 250 ml flask, 20 Celsius, and allowed to reach equilibrium, will any liquid remain? Okay, so let's think about how we have to approach this question. Okay, well, what I need to work on here is determining, like, how do I know if any liquid will remain? Well, I need to know what the vapor pressure is, right? I need to know what the vapor pressure is at this specific temperature. Well, I don't have, like, I'm not given that, so I don't know if I'm at equilibrium. I don't know if I'm at the saturation point or not. Like, I don't know if I'm at that max vapor pressure. So all we need to do here is figure out if I have 0.034 moles of liquid diethyl ether, I have a volume of 250 mils in my flask. It's at 20 Celsius. Can I use something to figure out what my pressure is of this stuff? If you recall, if you have the moles of something, the volume of something, and the temperature of something, you can easily use the ideal gas law, PV equals nRT, to figure out what the pressure is. So we're going to be into those for quite a few of these practice problems here. So we can actually work through and solve that. So we have PV equals nRT, right? You have to look up your R values from your AP equation sheet. Okay, they're on there. You have the volume of the flask. We could assume the volume of the flask is what the volume of the gas will be. We have the temperature, but remember we need to do something with that. We need to convert temperature into Kelvin. All right, so that's something else we got to do. We have the number of moles right here, and we have our R value from our equation sheet. So the only thing we don't have is pressure. Once you solve for the pressure, you can see where it is. We're using what? Diethyl ether, so we're here, okay? Find the pressure, see where it falls. Is it below the curve, meaning we're unsaturated at 20 Celsius, or is it on the curve? So take a second and see if you can use PV equals nRT. Remember, convert temperature to Kelvin. Remember, your volume has to be a certain unit as well. Be very careful. Look at your units in R, okay? So you know what unit your volume should be in. And moles could stay as moles. See if you can figure it out, and then we'll go from there. Okay, if you actually use PV equals nRT to solve this, you're going to find a pressure of 2,500-ish, depends on sig figs, 2,500 millimeters of mercury, which is the same as torr. Okay, a millimeter of mercury and torr is the same thing. The R value you have to use is the 62.36 liter times millimeter mercury over mole Kelvin. Units cancel out with all of this. Your milliliters turns into liters. You should have 0.250, and that gives you 2 sig figs for your final answer because moles has 2 sig figs here. So that's how I got that. So listen, if all of this evaporated, okay, this is the main takeaway here for this last example of this video. If all of this liquid diethyl ether evaporated, the pressure in this flask would be 2,500 millimeters of mercury, or 2,500 torr, right? But look at your curve. At 20 Celsius, what's the pressure allowed to be? Well, the pressure is only allowed to be like, I don't know, 450, 460. So you squirt the 0.034 moles of liquid diethyl ether in this flask, okay? Some of it starts to evaporate, right? Until we reach a pressure of 450 torr. Once we reach that pressure of 450 torr, no more evaporates, not allowed to, okay? So we can't have all of it evaporate. If all of it evaporated, the pressure would be 2,500 torr. Not the case, okay? So some will evaporate until the pressure reaches 450 torr, and we're saturated, okay? Will any liquid remain? Yes, all the rest of it, Okay, some evaporates to give you 450 torr, or yeah, 450 torr. The rest stays in the liquid state, so we cannot reach the pressure of 250. So you got to know what you're doing here with these PV equals nRT problems, which I'll continue with the next lesson here in the next video. When you do PV equals nRT, it's the pressure that would result if all of that 0.034 moles turns into a gas. Okay, how much pressure you're allowed to have when you're saturated is gained by looking at this chart, or this graph. Okay, that takes care of the first lesson on vapor pressure equilibrium, and the start of these practice problems. I'll do a couple more with you in the next lesson, the next video, and then you'll do a bunch on your own for practice. Okay? All right, guys, thanks.